Hi there, welcome to this lecture series on matrix algebra. This is lecture 14, part 2. In this part of the lecture, we'll continue our discussion on perpendicular projections. We'll take several examples here and we'll talk about projection on a vector space which consists of continuous functions. Okay, let's get started. So, this is our first example here. So we're given three vectors, and they are vectors of length 3, so they're in R3. So we have a V, and we have two vectors we call W1, W2. So we want to find the minimum distance to V from the subspace formed by span of W1 and W2. And we call this subspace capital W. Okay, so we see that we need to find the perpendicular projection of V on the subspace W. So let's assume the perpendicular projection is P here, and which is x1 W1 plus x2 W2. So it's a linear combination of W1 and W2 with coefficients x1 and x2. And these are the unknowns for our problem right now. We need to find these x1 and x2. Okay, so follow the formula we derived in the part 1, and we see that x1, x2, they are solutions to the system here. So the system is a linear system. It's A, x equal B, where in the A matrix, the position of each position, the element, and on the diagonal is just Wi dot Wi, so it's W1 dot W1, W2 dot W2, and then here we'll get W2 dot W1, and here's W1 dot W2. And the right hand side is the inner product of the V with the corresponding basis of the space W1 and W2. Okay, so then it remains to work out these inner products. So we see that to find A, we need to compute 3 inner product, and these two are the same. So this matrix is actually always symmetric, this coefficient matrix. And to find B, we need to calculate the 2 inner product. So after you work out all the inner products, we see that we have a system like this. And again, this is a symmetric matrix, and it's a 2 by 2, so we can solve it. And you carry out your procedure of solving this, and you find x1 and x2 are these two numbers. Now we can put x1 and x2 back into the linear combination formula and find this projection P. Okay, so what's this projection here? So here's the illustration, graphic one. So you have a subspace W, let's say consider 3D, and the subspace here is a 2-dimensional plane. And then you have another vector V, which is not in the plane in particular. So I'm finding the perpendicular projection, that is this vector here projected perpendicularly down onto the space W. So that's the vector P we just computed. Okay, it's in W. It is a kind of a shadow of this vector V in this perpendicular direction. Okay, so now this P is x1 W1 plus x2 W2. So we have everything. All of these we know them, so we put it in x1 W1, x2 W2, and you work out your scalar multiplication and the summation, and you get this vector. Okay, so again, recall this is vector P, which is this one. But then in the problem, we want to find the minimum distance, right? So the minimum distance is actually the distance of the vector from V to P. So we need to calculate p minus v or v minus p, which is and we already know what v is, and the p we just calculated, and we can work out this subtraction. So that's this vector here. Okay, and then the minimum distance will just be the length of this vector. So you can compute the norm of this vector, which will be square of each element, and then add them up and then take square root. Okay, so if you do that and you find out that it is 1/3, and then 1/3 would be the minimum distance of v from the space, the subspace W. Okay, so that's the answer, the solution to the problem. Okay, so let's take another example. So it's a similar problem. We are given the v vector and are given W1, W2, and we want to compute the perpendicular projection of v onto the subspace W. Okay. So we see that this is similar to the previous problem. Actually, we are only doing the first step just to find the projection. But in this case, there is some special property of the basis W1 and W2. And we see that if you take the inner product of W1 and W2, what do we get? Well, we get 1 times 1, which is 1, plus 2 times 1, which is 2, and then plus -3 times 1, which is -3. So you add them up, it's 0. So that means W1, W2, they're perpendicular to each other. So this is the special case where the basis of the subspace here, it's a perpendicular vectors. So then we know that for the system that we set up here in the general case, applying this special property, then we'll have 0 and 0, right? Then it becomes a diagonal system. So you can write out like the equation. Each equation will just have one term on the left hand side. The first equation will just be W1 dot W1 times x1 and equal to the right hand side v dot W1, and similar for the second equation. Okay, and then we can calculate, work out these inner products, all of these 4 with the given data, and then you will have this system. And then you can easily solve x1 and x2 from equation 1 and equation 2 separately, and that's what you get. Okay, so finally we can put them back into the formula for this perpendicular projection of v onto W. We call this P, which is just the linear combination with the coefficients x1, x2, which we just worked out. And then if you put in these numbers and put in W1 and W2, and that's the vector. And you can easily work it out and add these numbers up, and so I'll leave that as an exercise. Okay, so finally, let's take an example of perpendicular projection into a space of functions. Okay, so, and here is the setting. We consider the space V of all continuous functions on the interval from -π/2 to π/2. And we define the inner product, which is for function f and g, the inner product is the integrating the product of these two functions from -π/2 to π/2. And then we consider polynomials of degree 2, all polynomials of degree 2. Let's call it p of x, which will be c0 plus c1x plus c2x squared. This is a general form with the c's are coefficients, they're real numbers. So we want to seek one of these polynomials such that it best approximates the function cosine of x. Okay, so here's a graphic kind of a interpretation. So I know cosine of x, it's a periodic function. From negative pi over 2 to pi over 2, it covers a half period. It will be 0 and 0 here, and then it takes value 1 at x equals 0. So it's a smooth function looking like that. And I want to approximate that with some kind of a parabola, because it's a quadratic polynomial here. And the parabola, well, of course, we have to bend down. And let's say this red dotted curve is the graph of this parabola. Of course, it will not be exactly the cosine function, but we can choose the coefficients nice enough so that it becomes a pretty close approximation, and we want to find the best one. Okay, so we can now set up this problem in terms of perpendicular projections. So we have a function fx, which is cosine, and then we have three functions. F1 is 1, f2 is x, f3 is x squared. And then we see that the span of these three functions, f1, f2, f3, here will exactly be the span of 1, x and x squared, and that will be the space W, we call it, and which is the subspace of all polynomials of degree less than or equal to 2. Okay, and then by the theorem on vector space and projection, we know that we are finding this projection in terms of a linear combination, C1, C2, C3 being the coefficients, and these coefficients are determined by this linear system. So let's write it out. So these are the unknown vector, and the coefficients here, this A matrix Aij here would be just the inner product of Fi and Fj. Okay, so we write it out with the 3 by 3 case, and then that's the corresponding right hand side. Okay, and then there are a bunch of inner products to work out for this matrix, all the entries, and we make an observation that this is, again, we see a symmetric matrix, because this is the same as this, right? And this is the same as this, and this is the same as that. So we just need to compute like half of it. So 1, 2, 3, 4, 5, 6 inner product, and the inner product is this integral of the product of f and g over the interval negative pi over 2 to pi over 2. Okay, so work all of them out, and we plug in the inner product, the value we found. And this is the A matrix, and that's the B vector. Okay. And then you see that you can work this out and solve it, and you will get the coefficients C1, C2, and C3. Okay, so in general, we see that this is always a symmetric matrix, and also a general property is that if the bases are linearly independent functions, and that's of course is a property of a basis, then this matrix is invertible, and there is a unique solution for the C1, C2, C3. Okay, so that's all for today's lecture. We just covered 3 examples. I hope that is okay, that you enjoyed this lecture. In the next lecture, we will focus our attention on a special case where the bases are orthogonal vectors, and we'll talk about orthonormal bases. Okay, so I hope you enjoyed today's lecture, and I'll see you next time.